Why is okay? Good. See, like again, I want those to be the discussions we're playing with over and over and over again. If there's something where you're like, that doesn't seem obvious to me, then we're just going to explore it. Like I'm okay with exploring it. All right, why is this called a square? Why is this 10 squared? Well, we know that from an algebra perspective, this means 10 times 10, right? We also know from a geometry perspective, whenever I have a rectangle, I can do length times width gets me what?
The area.
Area. So it's called a square because the way that people would originally solve these problems is that they would build a rectangle that had a length of 10 and a width of 10. How big would the inside be?
100.
100, which they could get by making 10 going across, because it says 10, and 10 going down, and they could actually count the squares, right? So that's why this gets us 100, because I literally have 10 groups. One row is a group of 10. There's 10 in each row. So that's what forces this to be 100. Okay? So we went through that. That was one thing we talked about in the visual algebras. We're talking about how, like, hey, there's language that we are saying out loud, and we aren't paying attention to the fact that it's already using shapes. Like, we need to start using shapes if we want to understand these statements, because they are talking about shapes. So now let's go back to x squared. So x squared means what?
So it would be x times x.
X times x. That looks like another instance of length times width, right?
Mm-hmm.
So I can go off to the side here and I can make a little length by width rectangle where one side is x, the other side is x. How big is the inside?
X squared.
X squared. Like, it's literally saying whatever you tell me is the side, maybe it's 5, then the inside would be 5 squared. I'd have built a 5 by 5 square, right? It's in the language. So this is just saying, hey, we can talk about squares without putting dimensions on them. That makes sense all the time, right? If I said that I had a sandwich shaped like a square, you can imagine my sandwich, and I didn't have to tell you how big it was, because it's just an idea. Squares are fine. We can talk about squares. We don't always have to say specifically what their sizes are. Squares are fine, right? We've been playing with them since we were children. So this is just simply saying I have a square. Now, on this same idea, we went through in class how x really just means one group of x, right? So that right there is another shape. That's a length by width. That's a length of x and a width of what?
1.
1. So that's why in all of those pictures, I talk about them as rods or sticks, or there's little rectangles, right? X blocks. And then we also have units. What about 1? 1 is the same thing as 1 times 1, right?
Mm-hmm.
How big is that going to be?
Like a 1 by 1.
A 1 by 1 square, right?
Yeah.
Okay, good. So we've recognized that even if we're looking at algebra problems, there is the ability to represent that with geometry, right? So it's once we have that idea that it's in the language, that we're talking about shapes, that we're writing algebra, but that we are also able to play with them as shapes, that we begin to say, okay, let's start looking at problems like this. That right there is a bunch of shapes. It's an x square, which is an x by x dimension. It's 2 of these rods that are 1 by x's. And it's 1 single unit block, right?
Yeah. Yeah, that's like the visual representation of the numbers.
Perfect. Excellent. Now, if we wanted to do factoring, factoring creates 2 sets of parentheses. That's what we want as the answer for our problem, right?
Mm-hmm.
Well, this right here is a thing equals thing times thing. Again, this looks a lot like area is length times width, right? So that means all of these shapes are part of my area, and I need to organize them so that I can get a length and a width. So how can I do that? I could take my big X square, I could stack an X block next to it, I could stack another X block underneath it, and I could stick my unit right there. And then if I look at the length is my X sideways and 1, and my width is an X vertical and 1. So I've got length of X plus 1 and width of X plus 1. So this is factoring. Factoring is literally saying, I have a bunch of stuff. I want to organize it as a rectangle so that I can grab its dimensions, its length and its width.
So how did you get the X plus 1?
Yep. This right here is a width of X, right? It's exactly what you would do if it was any other numbers, right? All right, excellent. So now if you go back through the guided notes, you'll see that when we're trying to factor problems, we're trying to organize it into a rectangle because that's what would literally be happening if I was looking at these things. They would fit in a rectangle. They would fit in a rectangle that gives me length and width. The length and width is called multiplication. It's algebra and geometry. It's both happening same time, different ways, whatever I want, right? So it's why am I making it a rectangle? I'm not making it a rectangle. It is a rectangle. I'm recognizing that. So that's why we call it a quadratic equation. It's not that it's called a quadratic equation, so I use rectangles. It's rectangles make sense, so I call it a quadratic equation. You see the difference there? So we've now got the ability of factoring and algebra are all just able to be looked at as geometry as well. We've got many tools to understand these. So now when you go back through and you recognize that, like, I've been factoring things like this, that I was doing that because that's literally what it's saying. Like, I'm just following the directions. The directions are telling me these are shapes. So I'm playing with them like shapes. That if I look at a rectangle whose length is 2x minus 3 and whose height is x plus 2, then it has to be true that I get 2 x blocks here. Because if I went across an x and across an x, and then I went down an x, that size are 2x squares. Like, it has to be. Like, it's not just symbol pushing, it's literally what I'm being told is the thing in front of me. So I'm just decoding it. I'm just trying to build what it's telling me is there already. That this minus 3x's says I want to go over, well, now we're kind of playing with algebra land. We're going a -1 distance, a -1 distance, and a -1 distance, and then I'm going down x. Well, if I go down x, and I've gone -1 distances, -1 by x gives me 3 negative x blocks. We could shade them in. Like, I'm just building the rectangle it tells me to.
So you multiply across to get the area of, like, x and then 2x minus 3?
I mean, isn't that what you do when you make area?
Yeah.
Right? I mean, let's do this one. This one says I go down 2. All right, I go down 1, I go down another, 1 and 1. And then I go across 2 x blocks, right? So I go across 2 x, there's an x, there's an x, there's an x, there's an x for each. That gets me 4 x blocks, 1 by x. And then when I go down 2 but over 3, I get 6. 6 little -1s because they're -1 by +1 dimensions. Like, it's a rectangle. Like, it's what it is. So all those symbols and formulas and methods and procedures that you were doing in algebra, I'm not saying they don't work. I'm just saying if we don't know why they work, who cares? Right? Because, like, if it's just it works, then I'll just tell a computer to do it. If I don't know why it works, then I'm not in control of anything. Okay, so now do we feel like we have a better foothold on why all of these things are called squares, why all of these things are called it? Because this is historically accurate. Like, this is why they're called squares, because they are squares. This isn't just me, like, trying to make patterns happen in front of you all. Like, I'm literally, like, I'll show you my bookshelf. Like my bookshelf has like historical accounts and analyses of mathematics going back 2,000 years. Like it's what they are. Like I'm just the messenger. It's what it says.
So then you multiply 2x squared by -6 and then 4x by -3x, right?
Ah, now the question for that is why, right? The question's always why. It comes about from somebody, a mathematician, playing around and understanding the intricate workings of rectangles and discovering a truth about nature. You ready for this? This is the truth about nature. Give me 4 small numbers.
3, 7, 8, and 1.
8 and 1. Excellent. You chose these numbers, right? Now imagine that I'm building a rectangle. So when you said 3 and 7, that just means I'm going across how much?
10.
10, like 10 inches, right? Physical, go to the hardware store, build it, right? All right, what's the height here?
9.
9. Good. So this is a 10 by 9 rectangle, real life, real build rectangle. We good? Now take a look at what happens if I change my perspective of it. I'm going to just cut it into regions. I'm not changing anything. This is still a physical, real world rectangle. I just want to look at how big parts of the rectangle are. Keep in mind, this entire rectangle should be 90 big, right? 90 square units. Because you already told me that it was a 9 by 10, right? What's 3 times 8?
24.
24? 7 times 8?
56.
1 times 3?
3.
7 times 1.
7.
Now let's do some quick addition. 24, 56, 3, and 10, or 3 and 7. Does that add up to 90?
60, 70, and then, no, 80. 80 and 10, yeah.
Okay, so I'm just confirming again that this is not numbers on the paper. This is real world, real rectangle, hardware store, Home Depot level truth, right? That I can go build a rectangle. If I look at that rectangle and cut it up, I'll have smaller and bigger regions based on if I made the width smaller or bigger, but I will have a true rectangle, right? All right. Now becomes a place where a mathematician is not symbol pushing, we're recognizing patterns. Take a look at this. Can you do 3 times 56 for me?
That'd be 118.
118. Can you do 24 times 7 for me?
168.
Double check one of those for me.
Oh, yeah, the 150, I'm sorry, the 56 times 3 is 168.
Okay, so these are the same. Hang on. This is an area. This isn't even a length. This is an area. This isn't even a width. This is areas. This means if I multiply the size of areas times each other in the diagonals, I get the same thing. Geometrically, that makes no intuitive sense. That's not obvious. Why in the flip is the size of chunks of a rectangle multiplying to create the same thing in either direction? That's weird.
Yeah, I don't know.
That's okay. Like it's not obvious. Like I'm telling you from like straight, like take a look down here. Let's go back to this one. Does it make sense that the size of this thing times the size of that thing is the same is it going to be the same result as the size of this thing times the size of that thing?
I mean, no, I mean, they look very completely different.
They look wildly different. Like that's a weird pattern, but it worked with a random rectangle you chose, right? Do you think it works for all rectangles?
Yeah.
How do you know?
Because the property rectangle doesn't change. Like it'd be.
But to say I found one example of something in nature and to say all things must be like that is pretty bold, right? So what I'm walking you through here is I'm trying to walk you through how it is that like a mathematical mindset tackles these problems. We find something that looks absurd. We find an example of it and we're like, oh, that's weird. And then we dig in. We don't accept, we dive. Like we go, I can see that you finished the week 0 quiz. So you watched all those intro videos, right? About how math is a model of logic, math is an exploration, math is about diving deep and understanding stuff from within. Like this is the time to do that. So let's play a little bit. So here's how we played in class. I said, you know what? Instead of you choosing random numbers, since it seems to work for any numbers, let's start with variables. Let's look at it through variables so that I'm not tempted to think it's only specific numbers, and I'm not tempted to change the number's appearance by simplifying. If we do that, help me fill in the size of these regions.
So the first one would be AC.
Good.
And then BC.
Good.
And then AD.
Good.
And then BD.
Good. Now these are legitimately the sizes in the same way that if I gave you numbers, you would make a physical real world rectangle that fits it. Now let's look at the diagonal pattern. Multiply this diagonal.
Well, it would be AC and then BD.
Right, which I can reorganize to make it look like that, right? What about this one?
A,
I mean, we have A times D times BC, right?
Yeah.
Can you reorganize that?
ABCD.
Same thing?
Yeah.
All the time, right? Doesn't matter what A is, B is, C is, or D is. Guaranteed to be the same thing. So what this is one of my favorite examples of math in action. This is how math is done. Math is not equation pushing and symbol manipulation. It's understanding. So what we did was we started off with decoding. We made that look in a way that made sense to us. We used truths and observations. We made sure that those observations made sense on a deep level, because now we can see why do they come out to be the same. Because in the act of making the rectangle, everything gets scrambled, but also in the diagonals, everything appears once. A appears once, B appears once, C appears once, and D appears once, regardless of which way we're looking at it. So now what we can do is we can use all of these properties to solve our questions, our problems. Okay? So do you feel good on why everything works, where it comes from, why it makes sense? Now we could go and explain this to somebody who wasn't here.
So would it be like, so the squares across from each other, they each have one of the same properties. So
what properties? Make it specific.
So like if you multiply the area of each little square across, it would give you the same number.
Yes, right? It makes all of the dimensions appear together when you multiply diagonally. Why? I mean, we can see it in the picture because that's how the scrambling and unscrambling and combining has to work. It's an inherent property of rectangles. You can't break it if you try. Right? Okay. So now that we have all this observation, now let's try to tie it all together. So let's do an example problem. Let's do x squared minus 3x plus 2. What do we call this?
Quadratic.
How come?
We're trying to see if that fits, if we can like show it like in a rectangle.
There you go. Do you see how now you're in the story, right? It's a quadratic because it represents a rectangle. Excellent. Help me build this rectangle.
It would be x plus, so then on the top rectangle there, it would be X, and then X for the width and the length.
Okay, so this goes in that region. We place it, right?
Mm-hmm.
So that size is X squared. And you said that that means I have to have a length and width of X. I love that. Good. Where does this one go?
It would be like, so like 2 by 2?
Let's try it. 2 by 2 would be how big?
4.
I don't have 4. I only have 2. So again, let's go back to what it means, what it is. How do I draw this 2? All right, good. There's 1. There's another 1. In total, I have 2, right?
Mm-hmm.
I'm going to place them. Where do they go?
On the bottom.
On the bottom row where? There's 2 boxes I see.
In the right corner.
In the right corner? All right, so I'm placing my 2 over here with just 2 little boxes, right? There's 1, there's 1.
Mm-hmm.
All right, what are the dimensions? How tall is this?
1.
1, good. All right, so I've got a height of 1 and I've got a width of, what's my width together?
2.
2. All right, good. So I've got a width of 2. I've got a height of 1. Does that feel good? Okay, good. So now we're on our way. Let's double check something because I haven't been able to place these yet. And there are 2 regions they could go in. One could go up here. The other could go down here, right?
Mm-hmm.
Okay, so I don't know where my -3 blocks go, but that's 3 opposite blocks. Like I've got 3 physical tiles I'm trying to place. If I'm trying to figure out where they go, I can use the diagonal pattern because we know to make a real world Home Depot style box, these have to multiply to the same thing as this multiplies to, right?
Mm-hmm.
All right, x squared times 2 would be what?
2x squared.
2x squared. So behind the scenes of the rectangle, this, whatever these mystery numbers are, have to multiply to 2x squared. So I'm looking for 2 mystery numbers that multiply to 2x squared and that use up my full -3x. What are those numbers? X and 2x? I don't think those add up to -3x. They add up to 3x, they just don't add up to -3x. What do I need to change?
Be -4x and x.
I don't think those will multiply to 2x squared. I think you're really close. I just think you're missing a detail that makes them add up to -3x. What if we made these negative? Doesn't that work?
Oh, yeah, because it would turn into positive, yeah.
When they multiply, yeah, right? Doesn't that work?
Yeah.
Okay. So that means I can place -x here and -2x here. That'll complete my diagonal pattern. Now I just need to go about finding dimensions. So let me erase the dimensions and let's just try finding them from scratch. What dimensions work?
For the -3x.
No, there's no -3x in my diagram anymore. I split it up. I used the tiles to fill in the gaps. So I'm looking for the dimensions now. I'm looking for lengths and widths.
Oh, you mean like the length and width for each small rectangle?
I mean, that's what we want to do if we want to factor is make it multiplication. Multiplication's lengths and widths. So yeah, I want lengths and widths.
Well, then for the top one, it would be x and then x.
This one here is x.
The one on the for the length for the
This one's x.
yeah.
Okay. Keep going.
I mean for the -2x, so it'd be -2 as the length, and then -x as the width for the one on the right.
Like that?
Yeah.
-x times x, I don't think gets us -x. And I don't think -x times -2 gets me +2.
-1.
-1. Does that work?
Yeah.
If so, say it with confidence. Does it work or not work?
Yes.
That's not really confident. You sure?
Yeah.
Okay, good. I just want to make sure that it makes sense to you. Okay, so what you're telling me is that if I have a x square, a physical x square, 3 x blocks, and 2 unit blocks, I can rearrange all of those to form a rectangle whose dimensions are x minus 1 by x minus 2. That's what you're telling me. That's what it is. You want to make that physical? Here's the physical. It's a square. We can make a literal x by x square. Here are 3 opposite blocks where I have 1 opposite block on top, 2 opposite blocks on the bottom. That makes 3 in total. If I grab those dimensions, that's -1 and -1. That's -1 because they're opposite blocks. And then if I say, okay, -1 times -1, that's going to give me a positive block and then another positive block. And there you go. There are my 2. There are my 3 opposite blocks. And there is my x square. Organized in a way that gets me a length and a width. Now, if you learned in algebra something called the AC method, you hear about the AC method in algebra? Yeah, it says take this number in front, this number in the end, multiply them, and begin a big, long process that makes no sense, right?
Yeah.
Okay, cool. Now, do we understand why we would multiply the 1 and the 2?
Yeah.
Because it's a truth about rectangles, right?
Yeah.
So it makes sense that we would do a truth about rectangles when working with rectangle problems that are called rectangle problems, aka quadratics, when we're trying to make things into rectangles, because it's rectangles. Like, it's all rectangle. It's all rectangle. Like, I want this all to make sense. I don't want us to be able to just do it. I want us to be able to be like, oh, crud, like I actually learned something about the universe that I didn't know. And that's that there are patterns within rectangles, always, forever. So that level of understanding is what I want you to fight for each one of the topics. So I'd like you to go back, I'd like you to walk through those lectures, and I'd like you to find questions that you have where you're like, that happened, I don't know why. And I want you to bring those why questions to me before class, after class, office hours. I'm here till like 3, like we get lots of time, but I want you to be like, this now makes sense to me from like a core, like I could explain this to somebody, the why, or I have a question and I'm going to bring that question in. Okay, I'm totally on board with it, but don't do a single other practice problem that's just, I saw it happen this way before, so I'm going to do it this way. None of that will work in this class. I promise you, it gets too overwhelming too quick.